Okay, recall the formula for the sum of a finite geometric series okay, and that formula was S sub n equals, up in the numerator, a minus a r to the n power over 1 minus r. And r can't be 1 because you'd have division by 0. Okay, and we said you could factor out an a. Some authors do that, and you'd still have 1 minus r to the n power over 1 minus r. Okay. Notice in this formula, this is just n, not n minus 1. That's a common error. Okay, that is for the sum of a finite geometric series. Finite means it has an end. They might write it as an infinite with the dot dot dot, but as soon as they say find the sum of the first 20 terms or the sum of the first 15 terms, then they've made it finite, okay, by chopping it off. So this would be the formula you'd use for a finite sum of a finite geometric series. Okay, today we're going to talk about the sum of an infinite geometric series. Okay, the sum of an infinite geometric series if the absolute value of your ratio, the absolute value of r, if the absolute value of r is less than 1, then the sum equals S, and there's no n on it because it's infinite. The sum equals a over 1 minus r. A is the first term, r is the common ratio. That's if the absolute value of r is less than 1. If the absolute value of r is greater than or equal to 1, then no sum exists. Okay, so let's look at an example. Say I give you a series 2 plus 1 plus 1/2 plus 1/4 plus 1/8 plus and dot 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 to show that it continues and it's infinite. And I want to know, is there a sum? Okay, first you want to figure the ratio, and the ratio would be 1 divided by the previous term, 1/2 divided by the previous term, 1/4 divided by the previous term. Take 1/4 divided by 1/2. Remember, when you divide fractions, take 1/4 divided by 1/2. You're going to invert and multiply. 1/4 times 2 over 1, which would also be 1/2. So the common ratio is 1/2. Is that absolute value of that less than 1? Yes. Then you can find the sum. S equals a over 1 minus r. And S equals, our a value was 2 in our series, and 1 minus 1/2. If you simplify that, you'd get 2 over 1/2 divided by 1/2. Invert and multiply. 2 divided by 1/2. Invert this fraction. 2 times 2. And the sum of our series is 4. So the sum of that infinite geometric series would be 4. If we look at another example of an infinite geometric series, say I give you the series 5 plus 10 plus 20 plus 40 plus. And if you took, figure the ratio, 5 divided by the previous term would be 2. 20 divided by the previous term, 10 would be 2. 40 divided by the previous term, 20 would be 2. Common ratio of 2, and is that absolute value less than 1? No. So on this one, you would say that no sum exists. Okay, because the absolute value of the ratio is greater than or equal to 1. Okay? Okay, so those are just two examples of the sum of an infinite geometric series. The next thing the author will do is use that formula and use it to take a repeating decimal and figure out what the fraction is for that repeating decimal. Okay, so let's look at an example. Say they ask you to write the repeating decimal as a fraction in lowest terms. Remember, everything has to be in reduced form for your fractions, so they want it in lowest terms. And let's say I give you the decimal 0.4, and the bar above it means it's repeating. What I like to do is I like to show it repeating at least 3 times, and then you do need the 3 dots to show that it continues on. And we can write this as the sum of an infinite geometric series. You can write it either horizontally or vertically. If I write it 0.4 plus 0.04 plus 0.004, and then you need a plus sign and 3 dots to show that that continues on. If you would divide 0.04 divided by 0.4, you get 1/10. If you take 0.004 divided by 0.04, you get 1/10. Common ratio is 1/10, so the absolute value of r is less than 1, so yes, you can find the sum. So s equals a over 1 minus r. So a would be 0.4, the r would be 0.1, so you get 0.4 divided by 0.9. You can multiply by 10, okay, and move the decimal over one place on the numerator and denominator, and you end up with 4/9. And you can check that on your calculator. If you take 4 divided by 9, it should be 0.444 repeating. Okay. What if you had an example where it repeats in 2 digits? Okay, so like if I gave you the example 0.21 and it repeats in a block of 2, I still like to show it as a pattern repeating 3 times, and then you still need the dot dot dot. Okay, so we could write that as the sum of an infinite geometric series, 0.21 plus, now this time you're going to have 2 zeros and 2 1, plus now 4 zeros and 2 1, and then plus, you still need the 3 dots to show it continues. And if you divided this out, the common ratio on this one would be 0.01. So the ratio is less than 1. Absolute value of the ratio is less than 1. So yes, you can find the sum. Sum is a over 1 minus r. The a would be 0.21. 1 minus 0.01 would be 0.99 in the denominator. And you can multiply by 100, move the decimal over. You'd have 21 over 99, but remember the direction said in lowest terms. 3 would go into 21 7 times, 3 into 99 33 times, and if you divided that out on the calculator, you would get 0.2121 repeating. Okay. Now, that is actually one way to do repeating decimals, but the shortcut on that is to do it on the calculator. Okay, on the calculator, if you'll go back and put, and it has to go all the way across the screen on the calculator. I think you need at least maybe 12 4s going across the screen. Type that in on the calculator, and then use the math key. Like I said, I think you need 12 of these. Okay, and I'm not counting 2, 4, 6, 8, 10, 12 going across. Fill up that first line on the calculator. Then you use the math key. Okay, and then you want to go 2. It's going to show a little arrow, 2 fractions, and then you have to press enter. Okay, and then it should end up with 4/9. And if you do the same thing, do 0.21, 21, 21, go all the way across the screen on your calculator. Okay, and then do the math key, 2 fractions, and you should end up with 7/33. Okay, and that's the shortcut. Okay, the one thing that you need to go back and look at is back up here on the sum of an infinite geometric sequence. This part, I always teach this, and students just kind of accept that, but basically this is an infinite geometric series. We don't know what the last terms are on this infinite geometric series, but I just told you what the sum was. We were able to find the sum of an infinite geometric series, and that always bothers me when I teach that, because we don't know what the last terms are, but we've just found the sum. So you ought to think about that a little bit. This really is the sum, and what they basically say is here at the end, those terms are so infinitesimally small that they don't affect the overall sum. I like that keyword, infinitesimally small at the end. Okay, and that's it for today.